Hello everyone, welcome to the TIDC Poster Presentation Session 2021. My name is Vijay Rai. I am a third year PhD student at UConn. It is my pleasure to share some of the research information on development and testing of high ultra-high early strength concrete for durable bridge components and connections. Let's start with the motivation. Increased traffic loads have given rise to the need of bridge structure with increased load resistance. Increased traffic and the economical impact of disrupting the traffic flow have given rise to the bridge structures with enhanced durability, reduced maintenance, and quicker construction by utilizing the concept of accelerated bridge construction, which is known as ABC technology. Aging of infrastructure is very critical in US. More than 42% of the bridges are at least 50 years old and 7.5% of nation bridges are considered structurally deficient as per ASC report card 2021. And thus, there is a general need for the bridge structure with enhanced sustainability and lifespan. The main objective of this research is the development of cost-efficient, non-proprietary, high and ultra-high performance concrete mixes for the use in the bridge construction to address this need. It has many exciting properties that can be used for the closure pore connection and casting of bridge girders and decks like we can see in the figure 1. Ultra-high performance concrete in short form USPC is a cementitious composite with a relatively high amount of binder in comparison to conventional concrete. It is designed to use water to binder ratio of less than 0.2, achieves compressive strength in excess of 150 megapascal or say like 22 KSI, and addition of tailored discontinuous fiber reinforcement leads to significantly high ductility and durability of the cracked composite. Very high packing density of the matrix is the key for strength and durability properties of USPC. If we compare USPC with the normal strength concrete, the compressive strength is like more than 4 times greater. It is very resistant to freeze thaw, hot and humid, and marine environment. It requires less maintenance, and life of USPC can be expected to more than 200 years. However, the cost is main hindrance that limits the use of USPC. For example, commercially bagged USPC cost like $2,000 per cubic yard, which is like 20 times greater than normal strength concrete. Now let's talk about the research approach. Talking about research approach, we have used locally available igneous rock basalt as an aggregate instead of using refined silica sand, which is very costly, removing silica powder from the matrix, and instead of that using undensified silica fume and recycled glass powder reduces the cost. Recycled glass powder reduces carbon footprint and it is also very environmental friendly. Use of locally manufactured and distributed steel fibers as complying to the American Buy Act. It reduces the cost of the fibers as it is the mostly expensive material in the USPC. It provides high ductility and high post-cracking strength of the USPC composite. Let's talk about the results now. As we can see in the figure 2 and 3, all the concrete matrices have exceeded the compressive strength of 150 megapascal while having a sufficient workability. Increase in slag replacement has slightly increased the strength and led to the decrease in workability, starting with 40% of the replacement. In terms of silica fume to cement ratio, you can see that the best workability and strength is at ratio of 20%. There are results of electrical resistivity and direct tension in figure 4 and 5 respectively. Let's talk about the electrical resistivity first. It is the graph of preliminary result of electrical surface resistivity over the age of USPC. The threshold limit for the low permeable concrete has been plotted here in the red line. After 4 days, USPC surpasses the threshold of 27 kilo ohm centimeter and continue increasing the resistivity until reaching a measurement of 1000. which reaches the detection limit of the equipment. This means that the pore structure indeed extremely densified with aging of the concrete, and this is the key property for long-lasting durability of the material. Now let's talk about the direct tensile test, as we can see in the figure 5, and it also shows the direct tensile test setup and the specimen. Direct tensile test shows great consistency, strain hardening behavior, and a tensile strength of up to 2 ksi, and ductile behavior indicated by a peak strain of more than 0.5%. Now, in conclusion, all the mixes have exceeded the compressive strength of 150 megapascal after 28 days. Direct tensile strength of more than 1.2 ksi, and strain at least more than 0.4% for all the mixes. The electrical resistivity for all the mixes has exceeded 30 kilo ohm centimeter after like 4 days, and we are able to reduce the cost by like 1/4 times the cost of current proprietary USB-C, which is the biggest achievement from this research. In the future, we have planned for extensive investigation of durability properties such as phase durability, shrinkage, surface resistivity in the newly developed New England USB-C. And also we have planned to study the fiber efficiency. As I mentioned earlier, fiber is the most expensive material that is included in the USB-C matrix, so we want to reduce the cost of fibers as well. So at the end, I would like to thank to UConn Advanced Cementitious Materials and Composite Lab, UConn School of Engineering, Connecticut DOT, TIDC, Still Like Concrete, Lafarge Holcim, and also I would like to thank to my undergrad support, my colleagues, and thanks to my advisor for the constant guidance to make this research successful. Thank you.